We're now going to start section 7.4, where we will discuss solving trigonometric equations. Before we begin a trig equation, I want to remind you that solving equations means to solve for your variable. For example, if we had the equation 3 minus 6x is equal to 0, and we wanted to solve that equation, we would need to solve for x. And so we would do algebraic manipulations to move terms from one side to the other. So for example, I might add the 6x to both sides, which would cause it to cancel over here, leaving me just the 3 and giving me a 6x on the right. Then the next step to solve for x would be to divide by 6. Our 6's will cancel and we'll be left with 3 over 6, or 1/2, for our x value. So what you're going to see as we look at the trig equations is very similar steps. The only difference is that instead of solving for an x, we're going to be solving for a trig function. So let's take a look at a very similar example. So our example says 3 minus 6 cosine x is equal to 0. And so this is the same example that we just worked, except that instead of having a cosine x, we had an x prior. All right, so our goal is to solve for the trig function. So in this case, that means that we want to solve this equation for cosine x. And so we want to ask ourselves again, what do we need to do to get cosine x by itself? And I'm going to do the same steps that I just did on my regular algebra equation that we started with. So I'm going to add the 6 cosine x to both sides. And so that's going to give me a 3 on the left and a 6 cosine x on the right. The next step, getting the cosine by itself, is to divide both sides by 6. And so we end up with 3 over 6 is equal to cosine. And I'm going to go ahead and simplify that fraction to 1/2. So note, up to this point, we haven't really done anything different than what we did in our earlier algebra equation. We added the 6 and the function to one side, to both sides, and then we divided by 6. So the difference comes in writing your solutions. So in our algebra equation, once we reduce this fraction, we're done. In the trig equation, we still have to find out what x is equal to. So the question becomes, what angle has a cosine value of 1/2? And so we either know from memory or we know from our chart of exact values that cosine at pi over 3 is equal to 1/2. So one of my answers is going to be pi over 3. Now, the other thing to keep in mind is that when you're dealing with your unit circle values, remember that you have several places where the cosine is positive and several places where the cosine is negative. So remember that cosine is positive in the first and fourth quadrant and negative in the second and the third. So this pi over 3 answer that we came up with is our first quadrant answer. It's an angle that lies right here, and we know that it does have a cosine value of 1/2 at that angle. But there's also going to be a second angle that will work because our 1/2 is positive, so we also will have a fourth quadrant angle. And so our book suggests that we simply take our angle and rotate down the same distance. And so if this angle is pi over 3, then this angle is going to be negative pi over 3. Now, they do make the comment in the book that you could have taken this second angle and rotate it in a positive direction and come up with 5 pi over 3. And that would have been an acceptable solution as well. Now, we're almost done, but the other thing to keep in mind is that remember that our trig functions are periodic, meaning that they repeat. And so this pi over 3 angle, let me erase this just for a second. All right, so this pi over 3 angle that we're saying is one of the answers is an answer. But if I were to take the angle and rotate all the way around and come back to pi over 3, that would also be a solution to this trig function. And likewise, if I take that angle and I rotate all the way around, and I rotate all the way around again, and then come back to that angle, that would also be a solution. And so we can see that there are many solutions to this trig function, not just these two. But these two form kind of the foundation. They're the basis for all the other angles. All the other angles are simply rotations on the two angles that we've already found. And so the book suggests that we write our final answer in this format. So I'm going to take these answers. I'm going to add 2 pi, which means that I'm adding 1 complete rotation. And then I'm going to multiply it by n. All right, and the book says n is any integer. And so in other words, what's happening is if n is 1, we're saying we're going to do 1 rotation and then get back to the angle. If n is 2, it'll be the 2 rotations like we saw in green. If n is 3, we'll rotate 3 times. And so they're going to suggest that we always write this plus 2 pi n on our answers, which is going to produce a comprehensive list of all of our solutions and not just stop with the 2 that are on the unit circle. Okay, and so this would be the answer to that trig function. Okay, so let's go ahead and take a look at a second example. Our example reads, solve the equation tangent squared x minus 1 is equal to 2. We're going to begin in much the same way that we did the last example. Our goal is to solve for the trig function, in this case, tangent x. So in order to do that, the first thing I'm going to do in my attempt to get tangent x by itself is add 1 to both sides. So that's going to give me tangent squared x is equal to 3. Now I know that to go from a tangent squared to a tangent, I'm going to need to take the square root of both sides of the expression. And so the square root of tangent squared is going to leave me just a tangent, which is what I wanted. And the square root of 3 is going to stay the square root of 3, but remember when you take the square root of a number, you have to consider the positive and the negative counterpart of that number. Okay, so let's think about places where tangent is equal to square root of 3. Now again, either from our table of values that we've been working from or from memory, we know that tangent is equal to square root of 3 at pi over 3. And so I can go ahead and know that that is one of my solutions to my problem. Now remember that tangent is positive in the first and third quadrants and negative in the second and the fourth. And so technically, because we have the plus and the minus here, we can consider all quadrants as possibilities. So pi over 3 would be the angle in the first quadrant. I'm going to go ahead and do what we did in the last example, and I'm going to rotate down and say that negative pi over 3 is another solution. Now, keep in mind that the period on the tangent function is pi. The period on the sine and the cosine function, like we saw in the last example, was 2 pi. Okay, so remember that we added the 2 pi because that was the period for the cosine function. So if we're talking about the tangent function, we're going to be adding pi times n. And again, we're doing this where n is any integer. Now, you may be asking yourself, okay, so why are we only looking at those 2 quadrants when we said very clearly that we could be in all 4? Well, keep in mind that if your period is pi, that you really only have to look from a distance of pi in order to find your solutions. And this plus pi n is going to take care of the rest of them. All right, so let me just kind of show you what I mean by that. So if we take this pi over 3 and I plug a 1 in for the n, remember that the n is just an integer. This gives me pi over 3 plus pi, which is pi over 3. Now, how do I write this with a denominator of 3? It would have to be 3 over 3 to make the 1 that sits in front of the pi. And so if we add these things together, we're going to get 4 pi over 3. Well, 4 pi over 3 is, let me go to a chart here. 4 pi over 3 is your third quadrant angle. And so see, we are going to get that if we do the pi over 3. We do the pi over 3 and we add pi to it, it's going to push me around and give me the third quadrant answer. All right, similarly, if we take the negative pi over 3, which is rotating down, so this is our negative pi over 3 right here, and if I add pi to that, it's going to push me around to this angle, so the 2 pi over 3. And so you can see that we are going to get all 4 of these answers that we were hoping to have simply by adding the pi. And from there, as we add pi in another cycle, it's going to cycle around and come back, like on the red line. If we add pi again, it's going to come back up here. And if we add pi again, it's going to come back down here. And so we're going to continue to get those cycles of those answers. So keep in mind that you don't necessarily always have to name all 4 of the quadrants. You just need to be sure that all of your angles are going to be represented. All right, our next example asks us to find the answers to the equation sine squared x minus sine x is equal to sine x plus 3. So again, if this is an equation in an algebra class and you have a squared, you're more than likely going to be moving everything to one side and then trying to factor it because it appears to be quadratic. So let's see if that will work here as well. So I'm going to try to get everything on the left. So in doing that, I'm going to subtract this sine x from both sides. So that's going to give me sine squared x. A minus sign and a minus sign make minus 2 sine. It's going to cancel over here and leave me just the 3. My next step is going to be to subtract this 3 from both sides. So I'm going to have sine squared x minus 2 sine x minus 3 is equal to 0. And again, I'm looking at this as being a quadratic equation. I have my first term squared, I have the middle term to the first power, and then I have a number. So my hope here is that I could take this and factor it into 2 sets of parentheses. So let's look at our first term. In order to make sine squared, we would have to have a sine and a sine. Let's look at our last term. In order to make 3, we would have to have a 3 and a 1. And there really is no other choice for me on that. Now let's work on getting our signs correct. We need the middle terms to combine to make a -2 sine x. And so let's try it this way. I'm going to put my negative and my positive in. I'm going to check with FOIL method and make sure that I have it right. First times first is going to be sine squared. Outside, we're going to be sine x times 1. Inside will be -3 times sine x. And the last terms would be -3. And so we can see that our middle terms would combine to make this -2 sine x that we were hoping for. So once we know that we have it factored correctly, then we're going to do just what we would do in an algebra class. We're going to set our factors equal to 0 and solve. So I'm going to take sine x -3 and set it equal to 0. And I'm going to take sine x plus 1 and set it equal to 0. Remember that we're solving for sine. So on the first equation, I'm going to add 3 to both sides. So I need to look for places where sine x is equal to 3. On my second equation, I'm going to subtract 1 from both sides. And so I need to look for angles where sine is equal to -1. Now, if you consider your sine graph for just a second, remember that our sine graph has this shape. It reaches to a high point of 1 and a low point of -1. So is there a point on this graph where sine is equal to 3? There's not. The sine graph doesn't go any higher than 1. So this part is going to produce no solution. There is no angle that has a sine value of 3. Now there is an angle that has a sine value of -1. And we can see that on our graph. We can see that the sine graph comes down and hits at -1 right here. And so what is that angle? Remember that these are our 5 key points. We start with 0, we have pi over 2, we have pi, and we have 3 pi over 2 right here. And so our angle will be 3 pi over 2. Remember that your period for the sine function is 2 pi. And we're going to do rotations of 2 pi, so we'll add 2 pi times n. Okay, so the last example that we're going to look at here asks us to solve the equation -2 cosine squared x plus 1 equals sine x. And we start to see a problem creeping into this because we have 2 different functions. We have a cosine and we have a sine. This is similar in an algebra class to you having an equation that looks like this, where you have an x and a y and you being told to solve it. And so it is much easier for me to solve an equation if I only have one variable in it. So the first thing that I need to do is try to figure out how to write this equation with only sines or with only cosines. So we've had this issue before where we have used the Pythagorean identity and we have manipulated the terms so that we can plug in for what we need. So in this case, I'm going to subtract the sine squared from both sides of the expression. So that's going to give me cosine squared of x is equal to 1 minus sine squared x. And so what that does is it gives me something that I can come right here and plug in for the cosine. So instead of that cosine, I'm going to be putting in the 1 minus sine squared x. And so my expression is going to look like I've got that -2. I'm going to do my substitution here. I'm going to add the 1 and set it equal to sine x. Okay, so once that's done, then we can go ahead and distribute our -2. So negative 2 times 1 is negative 2. Negative 2 times negative sine squared will become a positive 2 sine squared x. We have a plus 1 equals sine x. And again, if you look at this and you see that squared, you think quadratic, you know that everything needs to be on one side so that we can hopefully factor it. So my next step is going to be to subtract this sine x off of both sides of the expression. Okay, so I'm going to have 2 sine squared x. I'm going to have a minus sine x. And then my numbers, I have a negative 2 and a 1, so that's going to make a negative 1. Now that it's quadratic in the right format, we're going to see if we can get it to factor. So for 2 sine squared, it's going to have to be a 2 sine and a 1 sine. For a 1, it's going to have to be a 1 and a 1. And for our signs, we would need one positive, one negative. I think we would want the negative back here and the positive here. And you could check that by doing your FOIL method very quickly and easily to make sure that you have it factored correctly. Once you do have it factored, then you're going to take each of your factors and you're going to set them equal to 0. So subtracting 1 from both sides gives me 2 sine x is equal to negative 1. Divide both sides by 2. We're going to be looking for places where sine is equal to negative 1/2. On our second equation, we're going to add 1 to both sides. So we're also going to be looking for places where sine is equal to 1. All right, so let's deal with the negative 1/2 first. Okay, so remember that your sine function is positive in the first and second quadrant, negative in the third and the fourth. The easiest way to do this is to ignore the negative just for a second and ask yourself, where would sine equal 1/2 in the first quadrant? So we know that sine would equal 1/2 at pi over 6. And that's either a memorized value or that's from our table that we've printed out. All right, so there's your pi over 6 angle. Now, we do need that angle to be either in the third or the fourth quadrant. The easiest thing to do is going to be to rotate that angle down, just like we've seen in previous examples. So rotating it down the same amount is going to produce an angle that looks like negative pi over 6. Okay, and then remember that your trig function has a period of 2 pi, and so we're going to add 2 pi into this. And this is going to handle the rotations that come around and land on that same angle. Now, we do need to think about, though, whether that's going to include the third quadrant as well as we do that. So if we take this negative pi over 6, let me go back to my chart for just a second. All right, so if I go and look at my negative pi over 6 angle, which is going to sit here. All right, so that's the negative pi over 6, and we're saying add pi to it, so we're saying do a complete rotation. Where's that going to put me? So if I add pi, it's going to send me all the way around, and we're going to go right back to the angle. If I add pi twice, that's going to go all the way around the second time, come right back to the angle. And so the problem is that we're never going to land on this third quadrant answer that we need. So we need to figure out what that third quadrant answer is and reflect that with a separate equation. All right, so what is it? So we know that this is one of our answers. We know that pi over 6 would be the positive 1/2. Okay, and so let's kind of just sort of reflect these answers over. We're using the idea of the reference angle here. This would be an answer, but it is positive. and this would be the other answer. And you can see that this is a reflection of this, and this is a reflection of this over the y-axis. All right, again, the two at the top are positive, so we really don't want to talk about those. We've already done the fourth quadrant. We now need to do the third quadrant. Okay, and so you can use a 7 pi over 6, or you can continue to rotate in a negative direction, and that's what the book does. So the book will say negative 5 pi over 6, which is this distance from here to that angle. And then again, they're going to add that 2 pi in to the answer. So you have this as a solution. That's your third quadrant. You have this as a solution as your fourth quadrant. All right, let's deal with this last one here. Sine x is equal to 1. All right, that's probably easiest dealt with on your graph. There's your sine graph. We know that the sine graph is equal to 1 at pi over 2. And so we're going to have pi over 2 plus 2 pi n as a third set of solutions.